So I'm here to talk about the complexity of fair coin flip, and as was mentioned, we're going to use the dichotomy theorem that we just saw to argue about the complexity of coin flip. But I want to start with fair computation. So fair computation is the computational task that demands that the multi-party computational task that demands that if one party obtains output, then all parties obtain output. Okay? And this is a natural security requirement. We can think of things like signature exchange, where it would be very important. And unfortunately, a classic result by Cleve shows that fairness is impossible in general. And this kind of confirms our expectations about the world, meaning that if parties are exchanging messages one after the other, then it seems that it has to be the case that one party has an advantage over the other in learning the outputs. Okay, this is what I mean by our expectations about the world. I wasn't trying to be deep, but okay, so in a breakthrough result, Gordon, Hazai, Katz, and Lindell showing that assuming oblivious transfer, there actually exist functions that can be computed fairly. Examples include the OR function, the greater than function, and many more. So this was followed by a sequence of works trying to explore the landscape of fair computation. And one of the highlights was a complete characterization of every Boolean two-party function. Okay? So more generally, so I just want to highlight from this slide that all of these works assume the existence of oblivious transfer or general secure multi-party computation with a board. So unfair computation is assumed for these works. Good. So more generally, we can try and quantify the advantage of a party in learning the output by some quantity epsilon. And we can think of fair protocols as living on some kind of spectrum, where on one end of the spectrum we have a negligible advantage, so which corresponds to the completely fair or perfectly fair setting that I was talking about in the previous slide. Or we can relax it to some inverse polynomial advantage and get some partial fairness. So if we zoom into a specific functionality, so the specific functionality that I'm interested in, which is coin flip, so basically two parties are trying to compute a uniform random bit, it can be shown that, I'm going to talk about these results in a moment again, but just to give you the spoiler. So we know that there does not exist a completely fair coin flip with negligible advantage. And depending on the resource that we assume, so depending on the computational hardness or the resource that we have, we get different advantages. So for one-way function, we get a 1 over square root of r advantage, where r is the number of rounds, whereas if we assume OT, then we get a 1 over r advantage. Okay, so let me define coin flip, because it's the central thing it's the topic of the talk. So a coin flip is a two-party protocol that satisfies the following requirements. On one hand, we have correctness. So an honest execution always yields a common uniform output. And the security requirement states that no matter what the efficient adversary does, the honest party's output is epsilon close to the uniform distribution. Okay? So it's important to emphasize that no matter what the adversary does, in particular, even if the adversary aborts, the honest party has to output a bit. For instance, if the adversary stops communicating at some point in the protocol, then the honest party outputs a bit, and this bit has to be close to uniform. Okay, this is actually this is a defining characteristic of fair protocols in general, that honest parties output something no matter what. Good. So let's revisit what is known about the fair two-party coin flip, so R round fair two-party coin flip. So Cleve's classic result, which rules out general fair secure computation, states that the optimal bias, so the value of epsilon, is at least 1 over the number of rounds. Averbuch et al. Showed that assuming one-way function, there exists a protocol with bias, so the fairness advantage is 1 over square root of R. Okay, and we're going to call these kinds of protocols as trivial coin flips. Like, there's nothing really trivial about them. It's just that we want to differentiate them from the next types of protocols, which assume oblivious transfer and can guarantee bias, optimal bias actually, which matches the Cleve's bound of magnitude 1 over R. Okay, so this gives rise to the following natural question of whether non-trivial coin flips, so anything better than 1 over square root of R, requires some kind of public key cryptography. So what I mean by public key cryptography is things like oblivious transfer, public key encryption, key agreement that we just saw. So there is previous work on this exact question. There are black box impossibilities that rule out restricted type of black box constructions for one-way functions. I want to highlight something that is relevant to our work, that there is no, from these results we can deduce that there is no black box construction from one-way function for non-trivial coin flip, so optimal bias coin flip for constant number of rounds. Okay, so this is what is known about this question. So let me tell you what we show. So we show that constant round, non-trivial coin flip implies infinitely often key agreement. So the infinitely often we inherited from Ronen and others, so I'm going to pretend that it doesn't exist and blame them. Slightly more formally, what we show is that for some universal constant, and for every constant R, so number of rounds, non-trivial coin flip, meaning that 1 over c square root of R, which is better than the 1 over square root of R, gives you a key agreement protocol. Okay? So before I tell you how we show this theorem, I'm going to first define a key agreement. So a key agreement is a two-party protocol that satisfies the following desiderata. On one hand, we have correctness, meaning that the parties agree on an output with overwhelming probability. And on the other hand, the security requirement states that for every efficient eavesdropper, the eavesdropper can only guess the output by nothing better than random guessing. Okay, this is how we define key agreement protocols. And for the rest of this talk, rather to prove the theorem, we're going to combine the dichotomy theorem that Ronen was talking about together with our attack from last year that gives an efficient 1 over square root of R attack on multi-party coin flipping. Good. So this is what the talk is going to look like. So first I'm going to revisit the attack, our attack from last year, as well as the attack that inspired our attack, the Cleve Impagliazzo attack from 1992. This is not Cleve's result. I'd just like to emphasize that. And on the other hand, I'm going to revisit some of the elements that I'm going to need from Ronen's talk. And finally, I'm going to try and convince you that our result is true given these things. So let's start with the background. So first, some notation, fair protocol. So a fair protocol is a normal-looking protocol. Parties exchange messages one after the other. At the end, they compute some output. So in a coin flip, these two outputs are the same and are equal. But contrary to unfair protocols, these kinds of protocols have backup values. So what these backup values are prescribed outputs in case one of the parties abort prematurely. Okay? These backup values are not, they are not known. So Daisy doesn't know Donald's backup values, and Donald doesn't know Daisy's backup values. And usually they are only computed only after something goes wrong. But for us, it's going to be convenient to think that every time a message is received, the party computes the backup value. So again, Zi, these Z's, are the prescribed outputs in case a party aborts at some round. For instance, if Donald doesn't send the second round message, then Daisy outputs the value Z1. Okay, so now let's look at our attacks. Good, so let's start with Cleve Impagliazzo's inefficient attack. So the attack goes something like this. We're assuming that the adversary is party B. And the adversary is instructed to abort without sending message I+1 if he detects a gap between the following quantities. The magnitude of the gap is 1 over square root of r. And the quantities that are compared are, on the one hand, the expected value of the output given the transcript up to and including message I+1. And the other quantity is the expected value of the backup of the honest party, conditioned on the transcript, not including the message that is not being sent. Okay? Intuitively, this quantity captures the fairness gap that the adversary is trying to exploit. Okay? So now let me try to argue why this attack is inefficient and why it yields 1 over square root of r bias. So first, it's inefficient because it might invert a one-way function. Specifically, the transcript might contain a commitment to the function, to the output. So computing the expectation of the output on conditional on the commitment is equivalent to opening the commitment. What about the frequency of the attack? Is a gap going to even be detected? So I'm not going to talk about it in this talk at all. It's going to be, the attack is going to be triggered with constant probability. It follows from a fact about martingales, and I invite you to look at either the old paper of Cleve Impagliazzo or our way better proof from last year. Good. Finally, does the attack yield a 1 over square root of r bias? So yes, and the reason is that conditioned on the transcript, not including the message being sent, the backup value of the honest party and the message that is not being sent are in product. Okay? So the new message I am supposed to send is independent of the backup value of the honest party. Okay? This allows us to replace, so technically, this allows us to replace the expectation over here with an expectation that is conditioned on the transcript up to and including round I+1, and by averaging over all possible transcripts, we get the desired bias. So if you don't get the last step, why this equation implies a bias, it doesn't matter. It's not hard, but it's not trivial. What is important is that showing that there is no dependency between the backup or that this equation is satisfied gives us the desired bias. Okay? Okay, so now let me give you the template of our attack. So our attack from last year lives in the multi-party setting. For the two-party setting, it's not going to work, but I'm still going to present it because it's going to be relevant for establishing the key agreement. So I said in the previous slide that the attack is inefficient because we can't really condition on the transcript. So the natural thing to do is to condition on some function of the transcript. So again, the adversary is trying to detect the gap between two expectations where the conditioning is some function, efficient function of the transcript. So let's try and analyze this new attack. So is this thing going to be efficient? Well, it depends on f, obviously, because if f is the identity function, then it's not going to be efficient because it's just the previous attack all over again. What about the frequency of the attack? So the attack, for the same reason as before, is going to be triggered with probability, with constant probability. And finally, are we going to obtain a 1 over square root of r bias? Well, no, if the protocol is OT secure. So what I mean by OT secure is that the protocol is secure assuming access to oblivious transfer. So let me say a few more things about our attack and efficiency and the bias. So the way we argue about efficiency is that we want the output of f to be small. We want there to be few bits that describe the output. So a natural candidate is the backup values. We can condition the expectation on the backup values of the adversary, and if there are few of them, so constant or logarithmic, then the expectation is efficiently computable and the attack is efficiently computable, can be done efficiently. Also uniformly. So non-uniformly, yes, it's just a function that we can, but uniformly we can sample experimentally and get as close as we like to the exact value. So what about the bias? So the point is that if pi is secure in the OT hybrid model, then there is no function f that is informative enough to break the dependency. In other words, our magic equation from a couple of slides ago is not going to go through for any choice of useful f. Okay? So again, I need to emphasize that this thing only happens in the two-party case. In the multi-party case, we're working very hard to find a suitable f that will allow us to break the dependency and show that we can get the 1 over square root of r bias. Good, so now let me go very fast over the dichotomy theorem of Ronen and others. So let's start with the items that we're going to use. So Ronen first talked about decorrelators and then he talked about forecasters. I'm going to do the opposite and how they relate to FAIR protocols. So a forecaster is a machine that takes an input, a transcript. So in my case, I'm also interested in partial transcripts. So the forecaster takes the partial transcript of the protocol and outputs a prediction, a distribution over the probability space of 2 bits with the following indistinguishability promise that the triplet consisting of the backup values and the partial transcript is indistinguishable from the simulated values together with the partial transcript. And they worked very hard to show that every protocol admits a forecaster for every constant value of rho. So next, the decorrelator. So to say what a decorrelator is, I'm going to tell you again what a forecaster does. So the forecaster eats a partial transcript, spits out a distribution over 2 bits. There is an indistinguishability promise. And the decorrelator, the difference with the decorrelator is that the decorrelator outputs a product distribution, not an arbitrary distribution over 2 bits, but specifically a product distribution. Good. And finally, here's the dichotomy theorem without all of the caveats. So either pi can be transformed into an infinitely often key agreement, or there is a rho decorrelator for every constant rho. Good. So let's try and combine all of these elements to deduce that constant round non-trivial coin flip implies infinitely often. Yes?
So this will be existential
What does that mean?
If I give you a non-trivial constant round coin flip,
Yes.
Can you efficiently build me an infinitely open key agreement?
I guess not, because I don't know how to find the forecaster.
But it exists.
Yes.
But what's if that's point, right? I mean, you're not going to actually build the key agreement using this. It's just a lower bound, right? The point is to show that, right? I mean, that you couldn't do it without the key agreement.
So yeah, and the technical reason is we're using the forecaster to build the key agreement, and we don't know how to find the forecaster. Yeah. Good. So, okay, so I'm trying to convince you that non-trivial coin flip implies key agreement. So we're going to start with an attack and argue that if the attack doesn't work, then I can have a key agreement. Okay, so let me start immediately with the attack. So the attack uses the forecaster. Okay, the adversary has the machine at hand and is going to use it and is going to apply the template of our attack. So he computes the output of the forecaster on the partial transcript to try and detect a fairness gap between the quantities I was talking about earlier. Okay? So I claim that if this attack doesn't work, doesn't give the required bias, then there is a way to transform pi into a key agreement. Okay, but let me do the 1, 2, 3 analysis that I did for the previous attack, also for this one. So first, what about efficiency? So I'm assuming constant round, and the support of all the delta j's is small, is only constant number of bits, which means that I can compute these values non-uniformly, or I can experimentally approximate them. Non-uniformly I can uniformly I can approximate them. Good. What about the frequency of the attack? So here it's the fact about martingales, constant probability. This attack is going to be triggered. And finally, does the attack result in a bias? Yes, if the underlying protocol doesn't imply key agreement. In more detail, if there is a decorrelator for a variant of pi that I'm going to give you in the next slide, then our magic equation is going to work and we're going to obtain the desired bias. Okay, so what is this variant of pi? Yes, 5 minutes. Okay, thanks. What is this variant of pi? So the variant of pi, I'm calling it pi star. It's almost exactly like pi. The difference is that Donald, the honest Donald, now it's a different protocol, is running the attack in his head, the previous attack. So they're exchanging messages exactly like pi, and at some point, the little person, the little guy in his head is telling him, you need to attack now. So at this point, Donald just informs Daisy, you know what, I think we should stop now. Daisy outputs the prescribed backup value from protocol pi, and Donald outputs the output of the forecaster on the partial transcript that includes the message that he was supposed to send according to pi. Okay? We show that if the attack that Donald is thinking about in his head doesn't work, doesn't give you the 1 over square root of r bias, then pi star can be transformed into a key agreement by applying the dichotomy theorem of Ronen and friends. So let's look at the analysis very quickly. So we assume that pi star doesn't imply key agreement, which means by the dichotomy theorem that pi star admits a row decorrelator. What does that mean? It means that given the transcript, the outputs, so delta I plus 1, which is the forecasted value, including the message that wasn't sent, and zi, the backup value, are computationally close to a product distribution. Because it's not a forecaster, it's a decorrelator. The decorrelator breaks the dependence of the outputs. Okay? Computationally. By data processing, using a data processing argument rather, conditioned on the delta I, so we're applying the function to the transcript, the output are still computationally close to a product distribution. But now everything here has very small support. These are constant number of values of constant number of bits. And over there, we have a constant number of bits as well, which means that these values are not computationally close condition on the forecasted values. They are actually close in a statistical sense, which means that we get our magic equation, which yields a 1 over square root of r bias if the protocol admits a decorrelator, or in other words, the protocol does not imply key agreement. Good. So that was some very broad strokes and hand-wavy part of the analysis. So let me just summarize and give you some open questions. So we showed that constant round non-trivial coin flip implies infinitely often key agreement. The natural questions to consider would be, first of all, what about super constant round complexity? Well, we run into two problems with this. The first one is that the value of the expectation might not be efficiently computable anymore. But this is not really a problem because we have a way to fix it using the weak martingale paradigm from our attack. The second more important problem is that the decorrelator is only guaranteed to exist for a constant row, and this we don't really know how to handle. Again, ideally, we would like to show that what we suspect to be true, that non-trivial coin flip implies oblivious transfer. And finally, can we get rid of the infinitely often business? Thank you.